Hello everybody, I'm Vivek Shandilya from the Department of Computer Science at University of Memphis. Today I'm going to present a bit of our work in use of attack graphs in security systems. So this is basically going to be defining the problem and just giving you the gist of what is the state of art today, the technology, what we can do, and what are the problems and challenges that we are facing and how we are approaching that. So the outline of the talk is going to be, first I'll define the motivation, and then the definition, and I'll explain the theoretical foundations of this idea, and then the practical objectives. Then I will describe the state-of-art technology as of now, which we have surveyed extensively, and we have classified them and how the contributions are, and then I conclude with what we can and what we need to do. So what's the basic motivation? Today, all the computational systems are becoming more interactive with their environments, and whether they're big or small. This is the trend that is getting on, and as the behavior of the environment has an intrinsic non-determinism associated with them from the system's perspective, it's a very difficult challenge to predict all the system's behavior and the interactions, so that none of which should lead it to an unsafe state. So in this context, we have to analyze the security properties of the system for checking any violations, and then identify the vulnerabilities that can be exploited to get there, and prioritize which of the vulnerabilities we are going to address first. You know, as security experts, we have a limited amount of resource to spend on security to ensure maximum output as much as we can. So what exactly is attack graph? To define it, a set of values of systems defining parameters can be modeled as a state, and temporally, at one instant, the system is in one state, and a sequence of them we can consider as an execution or a run, and then any execution that leads to an unsafe state is going to be a failure scenario, and the set of all of it would be a scenario graph. And an attack graph is a scenario graph where the cause for the failure is not a benign internal fault, but it's a malicious external action. So this is the way in which we're going to perceive it, because there have been many attempts to define it as a graph based on the conditions and many other approaches, but it turns out that this gives us the best way to formulate the violations of properties. So, well, to just give you an example, to have a feel of it, I'm presenting you one small example of an attack graph. Let's take a very toy example, simple one. There are 3 systems, and one is trying to take the services, and the 2 are offering them. The first one, machine 1 is offering FTP, RSH, and SSH, while the second is offering FTP and RSH, and machine 0 is trying to access them. Here is a firewall which is going to let the traffic to and fro. So, see, any of the requests regarding FTP, RSH, and SSH would be allowed from this, but you can see how we can draw a graph of what are the possible way the interactions can happen. But if there is a SSH request for machine 2, then there is something funny going on. That's where an interaction has got some anomaly, and that's where we need to look at that. This is going to violate some kind of a correctness property of the way the system should behave. That's the way we are going to construct attack graph. So basically with this, and having a quantitative measure of the probabilities with which the transitions can happen, we can add parameters to the graph and then do analysis and then get some results out of it. So, but yes, that's fine. We can create a data structure like this and a system based on this. We can do that. But computationally, what is the scientific problem behind it? To address that, let me define in the next slide. Basically, this is modeling it as a Bucci automaton, which is a stream automaton. And this is just like any other NFA, but it has a set of initial states, not just one as in the usual case, normally a set of alphabet, and then the transition function. But then here there is no acceptance state in the traditional sense, but there is an acceptance condition. So this gives the power of expression of various properties that we can have. So how do we define a run with it? We are going to look at it as a sequence of states, and then the initial state should be one of them from the set of initial states. Then the present state and the present input will decide the next state. So it's like the Markovian model. So based on this, we are going to have the acceptance condition such that a state where a property is violated would repeat infinite times. So that's the idea. So with this, we can postulate and formulate many of the security violations. So just to give the theoretical foundation behind that, with that we can see, yes, this is the kind of an automaton we are dealing with. Now, what are the practical objectives? So we studied around 30 major works during the past decade in using attack graphs in the security systems. And during our study and critical analysis, these are the questions we are asking. What are the parameters of the systems that are used to construct the graphs? What kind of graphs are constructed and how the graphs are generated? Generating it manually is out of question. So how scalable is their automated generation methods are and the tools used? And how good is their visualization? And then what are the properties that can be analyzed using those graphs? And then after analysis, and what kind of recommendations that can be generated to fix the problem? Precise, implementable solutions. How much effective is that? This is one of the important parameters. And then, fine, and how have they actually evaluated their work to show us? So this is the basic survey which we did. And with that, we were able to classify the total, all the works based on these categories. Most of them were making contributions in either the methodology or the technology. And then in that, we are looking at the formal model used. Basically, it has to be a Bucci automaton, but they are going to adapt it in such a way that they are going to address some feature and some special attribute. So that way, and then the representation of the system parameters used, and what are the methodologies doing to do that, and then the graph analysis and the property formulation, because there have been very different way of formulating the properties, and that formulation decides what actually you can identify and what kind of violations you can detect. And then, of course, in the end, how do you formulate the response? And similarly, in the technology section, we are looking at the automatic graph generation, because how scalable it is, because you have 20, 30 hosts, makes no sense. 50,000 hosts, not bad, but still it has to be more as of today. And then graph analysis and violation detection, and then how they are visualized actually on the system. And then the response recommendation and how timely it can be implemented, and can we do it dynamically? So if an attack is going on, and then it is evolving or changing, and then if we can generate the graph and then have a dynamic analysis and then a recommendation to deal with it, that would be of some importance. Yes, there is a work in the direction too. So what exactly is the summary of state of art? What are the things that we can do? So here it is. So today we can do these things. Both the system parameters and the domain model parameters of the system can be used. Around more than 50,000 hosts can be modeled, and then information integration from different vulnerability databases can be done. And to deal with multiple kinds of graphs, and dynamic analysis and visualization is pretty good. But what are the challenges? The optimum cost-effective security measure with imperfect information is yet to be achieved. Generation of useful domain model from the network topology is to be done, and effective attack taxonomy for the attack identification, and an integrated security system based on this has to be developed. And this has been, which we are actually working on, which is going into 2 major papers. And it is a collaboration with Mr. Chris Simmons of Lipscomb University and my advisor, Dr. Sajjan Shiva, who is the chair of Department of Computer Science at University of Memphis. So thank you for this opportunity. Let me know if you have any questions.